the robot data as an input to that sub-VI. We've placed a while loop around all the code in that sub-VI with a 10 millisecond delay. And we've wired the condition terminal so that it runs forever. And lastly, we made sure that we have a shift register so that all the important internal state information gets captured. So if you were to test this out, you'd find that indeed the mechanism works fine. But your debug dashboard would no longer contain the right information. The reason why is that the debug dashboard gets only the data which sits in this shift register. And because we've taken this sub-VI out of the TeleOp, no longer is that data contained here. Although it's technically present in the typedef, it's not being written to anywhere inside TeleOp. It's being written to over here. And there's no mechanism to send the data from this loop back to the debug dashboard. So let's look at a way to make that happen. Well, the answer is global variable. We've seen global variables before. We know that's how we actually send information into the autonomous mode. So what we need to do is to place some important information into a global variable. Naturally, the information we need to place is the data that's in the shift register. So what we need to do is to take a copy of the lifter typedef and make that part of our global variable. So let's go back to our project window for a second. In the Project Explorer, under our team code, we see our robot global data. All we need to do is take our lifter typedef and drag it in onto the front panel of the global data. Let's just rearrange things a little bit because we obscured one of the previous controls, and give it the proper name. This is our lifter typedef. We save it, close it, and now we can drag that robot global data onto our lifter state machine. So remember, to select the type of global variable we want, we just click in the middle and choose the right global variable. So now we've got this global variable here that we can write to. The question is, where do we want to write it? It has to be inside the loop, otherwise it's not going to be updated. And the best choice is on the far right after the cases have executed. So we take the latest value, which is just about to be put in the shift register, and we put it into the global variable. This will ensure that whatever states, whatever values are available in our state machine have now been placed in that global variable. The whole point of doing this is so we can put this into our debug dashboard or anywhere else we need to read those values. So we select our global, we copy, we return to our debug dashboard, and we no longer want to be pulling that information out of the robot data because, as we just saw, it's not there. We'll do a paste. We want to read from this global, so we right click on it, change to read, hook it up to this unbundle by name. We just need to reselect the values, and immediately when we run this, we'll see that the latest information from our state machine is automatically available in our debug dashboard. And later on, we'll see that we can write these values into the dashboard program, which will be running on our laptop when we're in competition. But in the meantime, this is still a very useful tool to be able to do debugging while we're deploying. So now that we've seen how we can use global variables to write from one location to another, I just want to make a very quick note to talk about race conditions. Race conditions essentially mean you have to be careful that the same data doesn't get written to in two different places at the same time. What we've done here, where the lifter VI is writing into the lifter global and the dashboard VI is reading from the lifter global, is perfectly safe. It's safe because it's only being written to in one place and it's only being read in one place. Again, it's safe to read from multiple locations. It's only risky to write in multiple locations. Another point I want to make about the example we just saw is that it's particularly simple because the lifter does not get any information from any of the other loops. Sure, the type-def contains the device references. Those are defined in the begin VI, but none of the other loops that run in parallel with the lifter need to send information to it. However, it's very common that your parallel loops do need to talk to each other. So let's investigate a way that we can modify this code to make that necessary. What we're going to do is add a manual override mode, where a joystick button is going to turn off the state machine, put it into a manual mode where the joystick axis is going to move the motor speed of the mechanical lifter. This is going to make this example a lot more complicated, not only because we're adding states and modes to this state machine, but also because the Tele-Op.vi is where we're reading from the joystick. And that's where we need to write information that's going to come into the lifter. So let's look at how we're going to do that. Well, let's first edit our Tele-Op.vi to extract the information we need. We're not going to get rid of the arcade drive. We're just going to move it down a little bit. So we're going to read from a third axis. Let's choose axis 5. And we're going to read from the buttons. Basically, what we're going to do is treat button 1 as the manual override button for the mechanical lifter, and axis 5 as the speed command. The way that I'm going to recommend we approach this is to create a new global variable, which of course is based on a type-def. We're going to call the command signal. And the command signal is going to be a cluster which contains all the possible commands you might want to send from the TeleOp to any of your other parallel loops. So in this case, we've got just the mechanical lifter. But in your robot, you may want to send commands to a variety of other parallel loops. Perhaps you have some sort of steering loop, which is parallel, traction control, propulsion, functional mechanism, any sort of other type of loop that you might have in parallel. You want to put all the commands together into one global variable. And it's important to remember that that global variable can only be written to by the Tele-Op.vi. However, it can be read by all of the different parallel loops. So let's create it now. We'll go to the front panel, create a cluster. And I'm going to add first the manual lifter speed command, which we'll put into the cluster, and a Boolean, which we'll call manual lifter override. Put that into the cluster, set our cluster to auto size arrange vertically, turn it into a type-def, edit, customize control, change it to a type-def, save it. We'll call this our command signal type-def, close it, and save it. Change its name to command signal. And lastly, we want this to be a global variable. So we're going to just select the type-def we just created. See, it's a type-def. Select it, cut it, and then put it into our global variable. So we'll go back to the Project Explorer, go back to our global data, and just paste it in. So in our Tele-Op.vi, we're going to drag our global data in, change it to be the command signal, and here we're going to write into this. In order to write into it, we're going to do a bundle by name. Which is going to go into the global variable. But remember, we always need an input cluster for this. So we'll just create a constant of our command signal. And the only thing that this is doing is helping us define the data type of our input cluster.